Good evening, physics friends, or good morning. I have no idea when you're watching this. You may be watching it like the hour before you're supposed to be in class with me, but that's okay. Make sure you have a pencil and a piece of paper when you're watching this, or print out the notes. Today's lesson is on where and when. So we're going to be talking about a few key terms here. The first thing we're going to be talking about when we start defining motion, like how do we move? Motion is all relative, and which is basically, if you've ever heard of Albert Einstein's relativity, you'd know that, well, the word relative comes from the term relativity. So relative to what? What does that mean? We're going to be talking about a couple of terms called vectors and scalars. And we're going to be talking about a couple of terms, time interval and displacement. So those are the three big things that we're going to be talking about today. And I've got a few videos to show you as we go through them. They're a lot of fun. They're pretty cool, actually, if I do say so myself. So let's get started. The first thing I want to talk about is frame of reference. Your frame of reference is how you view a problem. Maybe I'll redo that. It's how you observe an event. That's a better way. How you observe an event. Let me get more into this. I've got a really cool video that was made by MIT. Gosh, I think it was like 50 years ago. It's one of my favorite videos of all time. And you're thinking, oh my gosh, this thing's 50 years old. How can it be any cool? Let me show you. It's very fun. We aren't going to watch all 8.5 minutes of this thing, but we're going to watch a little bit.
We are used to seeing things from a particular point of view. That is, from a particular frame of reference. And things look different to us under different circumstances. At the moment, things look You look peculiar. You're upside down. No, you're the one that's upside down. No, you're upside down. No, I'm not. He's the one that's upside down, isn't he? Well, let's toss for it. All right. Okay. You lose. He's the one that's really upside down. You better come into my frame of reference now. My frame of reference was inverted from what it usually is. That view of things would be normal for me if I normally walked on my hands. This represents a frame of reference.
He says this represents a frame of reference, but what he's really talking about is this represents X, Y, and Z. So when we get talking about like geometrically, like this represents the X-axis.
Three rods stuck together.
Oh, I can't draw on this. Well, maybe I'll come around here. He's saying that one direction represents the X-axis, another one represents the Y-axis, and then another represents the Z. So these are three right-angled bars that say this represents a frame of reference, meaning that this direction is X, this direction is Y, and then this direction is Z.
Right angles to the other two. Now I'm going to move in this direction. You see the frame at the same spot on your screen, but you know I'm moving this way because you see the wall moving this way behind me. But how do you know that I'm not standing still and the wall moving? It was the wall that was moving. Now the wall has disappeared, and you have no way of telling whether I am moving or not. But now you know that I'm moving. The point of this is that all motion is relative. In both cases, I was moving relative to the wall, and the wall was moving relative to me. All motion is relative, but we tend to think of one thing as being fixed and the other thing as being moving. We usually think of the earth as fixed, and walls are usually fixed to the earth, so perhaps you were surprised the first time when it was the wall that was moving and not Dr. Hume. A frame of reference fixed to the earth is the most common frame of reference in which to observe the motion of other things.
So that's where we're gonna stop this right now.
This is
We
the
just
frame
talked
of
about your
reference
frame
that
of
you're
reference. The most typical frame of reference when viewing an event is from standing still with respect to the earth. Somebody standing on the earth observing something. I'm going to show you a couple more. Which was my next one I wanted to show you? Assumptions. This is a good one. So you see this right here. You're looking at this problem from a typical frame of reference of looks like you're on the floor looking up at this person. What you're witnessing is what's called forced perspective. You don't know, you're forced into this frame of reference by where the camera is fixed. And you don't know that this cup back here is a huge, it's just farther away. This is how the actual Lord of the Rings was filmed. When they had people that were hobbits, they're actually real, like Ian McKellen, the guy that played Gandalf, and Frodo, when they were talking to one another, Frodo would just be way far away, so he looked small, and they would just look, there were certain spots they would look, but they were actually looking past one another, but it looked like they were looking at each other. Forced perspective, a different frame of reference. Here's another one. This one's a fun one. This is from inside of a ship. And now you're viewing this from the perspective of the ship. Very fun. So that one was a frame of reference of. Oh gosh,
Hi,
these are great.
my
These
name is
videos are
Johnny
so
Lee.
much fun. I could spend a long time going through these videos with you. If you're at all interested, I encourage you to check them out. They're a lot of fun. A coordinate system. A coordinate system is a system which gives. A system which gives positive and negative directions along with magnitudes, meaning how much. Like in this coordinate system here, you can clearly see this is the positive direction, these are the negative direction, positive direction, and each of these squares represents 1. The origin is where 0 is located. So for instance, if you look down below here, I've got a picture of people running. The 0 is located right here. Here is the origin. Going to the right is going to give you positive amounts. And if you look at this one right below here, here's 0, that origin again, but this time you can move in the left and go negative. So you can have a negative displacement and you can have a negative distance. Position. How far you are you're away from the origin. Distance. Well, that's actually how far you are away from the origin. Position. I gotta look that one up. What did I write for position? Looks like position and distance are the same thing. Let's talk a little bit about what are called vectors and scalars. In science, there are two, well, in physics specifically, there are two fundamentally different types of measurements. I'll give you an instance. For instance, force is one type. 5 pounds, 20 pounds, 100 pounds, 200 pounds, or what's another? Time. There's a fundamental difference between these two. Another example, let's see here. Acceleration. Temperature. Velocity. Speed. These ones are tricky. Here's another tricky couple here. Displacement. Distance. Mass. Luminous intensity. Amount of substance. Current. A vector, what a vector is, I'm going to give these a different color here. Let's pick this one. No, that's not a good one. What a vector is, it's a measurement that has magnitude and direction. Direction meaning like force. When I tell you 5 pounds, are you pushing down on this person at 5 pounds? Are you pushing up on this person at 5 pounds? Are you pushing to the left at 5 pounds? Or are you pushing to the right at 5? Or are you pushing at an angle? When you push on something, the angle at the direction with which you're pushing means everything, along with how hard you're pushing. Acceleration. Are you accelerating forward? Are you accelerating backwards? Are you accelerating in different directions? Your velocity. 55 miles an hour north. My speed, 55 miles an hour. A scalar is just a measurement that has magnitude. Like time. It doesn't matter if time is going if time is going north, forward, south, backwards, to the right, to the left. Time is still time. Temperature is still temperature. Speed, distance, 5 feet. Displacement, 5 feet west. Mass, luminous intensity, amount of substance, electrical current, none of these depend on what direction they're going. And I don't mean direction like positive or negative, like time. I'm running time forward, I'm running time backwards. No, that doesn't make a difference. A vector is a measurement that has both magnitude and direction. Maybe you recognize this, maybe you don't.
I'm applying for a new villain loan. Go by the name of...
This is from the movie Despicable Me.
It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah!
Direction and magnitude. And it's commonly referred to by an arrow. When we talk about forces, we're going to be drawing arrows to represent which direction. The larger the arrow, the more the force. The direction of the arrow is what direction it's applied. The last two are time interval and displacement. Here we're going to have a couple of equations. Well, they're not really equations. The first one, delta t. This little triangle thing right here means delta. It's a Greek letter, which means change in. I'm sure in chemistry class you learned this. This is T sub F. So this little letter below it, we call this a subscript. A subscript, this is T sub F, which means it's the final temperature. Or, I'm not sorry, final time. We're dealing with time here. And the T sub I, and that's how we typically will say this, subscript, this represents the initial time. So to find a time interval, you just take the final time minus your initial time. For instance, you go to run a race. Let's say you're in the 400-meter dash, and you finish it at 12 o'clock noon. You started it at 11:59. How much time did it take? What was the change in time? 1 minute. It took you 1 minute to do this. So you take the final time and the initial time. A lot of times in physics class, the initial is going to be 0. So it makes it really simple to figure out the delta time, because if this equals 0, then the final time is the delta time. And displacement, you saw before that we have displacement and we also have distance. Displacement is how far you are from your initial position. And you have to have a direction. This must have a direction. A lot of times, if it's positive or if it's negative, that will denote direction if you're talking about a one-dimensional thing. Forwards, backwards. Positive, negative. Sometimes you'll have to have things like up or down, or you may have to have north, south, east, or west. So you must make sure that you have some direction when you're talking about displacement, because displacement and distance, they look really similar, but they're not. Distance is a scalar. Displacement is a vector. Has to have a magnitude and direction. And that's all I have for you for 2.2, where and when. Frames of reference. Go on that YouTube video. We're going to watch a lot of them in class, but check those out.